Welcome to episode 109, Spotlight, Security and Privacy Engineering Principles focusing on Control SA-8. This control reminds us that protection begins at the drawing board, not after deployment. Security must be built into the architecture itself, woven into every design choice rather than layered on as an afterthought. Systems that start secure stay stable longer because their defenses are structural, not decorative. Privacy also depends on early design. It cannot be bolted on once data has already been collected or shared. Building security and privacy into design creates predictability, reliability, and trust. It ensures that resilience is engineered, not improvised.
Next, systems should default to secure settings and demonstrate fail-safe behavior. Secure defaults mean new installations or configurations start in their safest form, requiring deliberate action to weaken protection. Fail-safe design ensures that when a system error occurs, it moves to a secure state rather than a permissive one. For instance, if a firewall policy cannot load, it should block by default, not open all ports. These design patterns accept that failure is inevitable and plan for it. Users should not have to know security to benefit from it. The system should protect them automatically through thoughtful defaults and predictable, safe error handling. From there, defense in depth establishes multiple, independent layers of protection. No single barrier can block every threat, so overlapping mechanisms ensure that one failure does not expose everything. Each layer operates autonomously. Network segmentation protects even if authentication fails. Encryption safeguards data even if access control breaks. For example, a breach in one service might still be contained by database isolation and audit monitoring. Independent layers multiply resilience by requiring attackers to defeat several unrelated controls in sequence. Defense in depth is less about redundancy and more about diversity. Each layer compensates for another's weaknesses. Equally critical are clearly defined trust boundaries early in design. A trust boundary marks where data or control transitions between entities with different privileges or reliability levels. Examples include user input entering a web application or an external API feeding internal systems. Defining these boundaries clarifies where validation, authentication, and encryption must occur. Without explicit boundaries, developers may assume trust where none exists, allowing unverified data to cross into sensitive areas. By marking boundaries in architecture diagrams and code interfaces, teams visualize the edges of confidence. Clear trust demarcation helps enforce consistent policy across components and prevents subtle privilege leaks.
Documentation is another foundational expectation. Secure by design documentation captures the rationale behind protective choices, configuration assumptions, and dependency decisions. It answers not only what was built, but why it was built that way. This record becomes invaluable when systems evolve or when auditors and successors must verify integrity. For instance, explaining why a particular encryption library was chosen clarifies maintenance requirements later. Documentation transforms individual reasoning into institutional knowledge, making security decisions transparent and defensible. Without it, good design erodes over time, replaced by guesswork and inconsistent interpretation. Writing down the why is as vital as perfecting the how. Closely linked is the principle of data minimization and privacy by default. Systems should collect only the data necessary for their purpose, store it for only as long as required, and limit access strictly. Privacy by default means users begin protected, not exposed. They must opt into data sharing rather than find out later what was shared. For example, an analytics platform should anonymize data automatically instead of requiring manual configuration. Minimization reduces the value of stolen data and the harm of accidental disclosure. These principles protect not only individuals, but also the organization's reputation, demonstrating respect for both compliance and human dignity.
Cryptography, when used, must be implemented correctly and provably. Correct use means applying trusted algorithms, proper key management, and validated libraries. Provable means the design can demonstrate that cryptographic protection works as intended through peer review or formal verification. Common failures arise not from weak math, but from misuse, hard-coded keys, insecure random generators, or poor certificate handling. For example, encrypting data but exposing keys in plain text cancels all benefit. Cryptography should be applied systematically with documented rationale and renewal schedules. When done right, it strengthens every other principle, safeguarding confidentiality and integrity even under partial compromise. Explicit rollback and recovery paths must also be built into system design. Security measures can occasionally fail, or updates can introduce regressions, so the ability to revert safely is essential. Rollback planning ensures systems can return to known good states without losing integrity or leaving data unprotected. For instance, if a new authentication module fails, operators should have a secure method to restore the previous version without bypassing controls. Recovery paths reinforce reliability, proving that security improvements do not risk operational paralysis. Planning for safe retreat is not weakness, it is the mark of mature engineering. Verification hooks, tests, checks, and proofs connect design intent to measurable assurance. Hooks can include automated unit tests for access controls, integrity checks for data validation, and regression tests for cryptographic operations. Continuous integration pipelines can enforce these checks automatically with every build. Verification confirms that protection mechanisms function as designed, and that changes do not silently weaken them. For example, a failing test when a developer removes input validation acts as an early warning. By embedding verification in engineering workflows, teams replace assumptions of safety with evidence of performance, sustaining assurance at the pace of development. Evidence of design decisions with clear rationale completes the engineering record. Collecting architecture reviews, design meeting notes, and test artifacts forms a traceable assurance trail. This evidence demonstrates that security principles were not theoretical aspirations, but implemented choices. It allows auditors, certifiers, and future maintainers to see continuity between policy and execution. For instance, a documented decision log showing threat mitigations per component connects control requirements directly to code. Evidence preserves accountability and reduces rework during compliance reviews. It proves that the system's integrity rests on verified design rather than verbal assurance. Metrics finally measure effectiveness through defect escape rates and rework frequency. Defect escape shows how many security issues reach production despite testing, while rework measures how often features require redesign to meet requirements. Decreasing trends signal maturing design discipline. If repeated rework occurs in the same subsystem, it may reveal unclear principles or inadequate training. Metrics convert engineering culture into data-driven improvement. They motivate teams to embed security habits so deeply that fewer problems surface later. Tracking these outcomes ties design quality to measurable performance, ensuring that secure engineering remains a living commitment, not a slogan. In conclusion, Control SA-8 embodies the philosophy that assurance is engineered, not added. Security and privacy principles must live in the architecture, source code, and decision logic of every system. When least privilege, secure defaults, and layered defenses guide each design step, protection becomes invisible yet effective. These principles deliver systems that fail safely, recover predictably, and respect the data they hold. In the end, secure engineering is not a separate practice. It is simply good engineering done with foresight and integrity. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.